Okay, who is that? Who is that? What does he say? To infinity and beyond? Yeah? Do you want to watch that movie?
Yeah.
Okay, we can watch it in a little bit, okay? Daddy's gonna do his film. Okay, you gonna play?
Oh, I have my new guy.
Here. So, precalc, chapter 11, section 4, it's limits at infinity. So, to infinity and beyond. The two basic problems of calculus is to look at the slope of the tangent line, which is the derivative. We've been talking about that. The other one is finding area under a region or a curve. So that's 11.5. So we're going to build up to that. But let's first look at, so the definition of limits at infinity is if f is a function and L1 and L2 are real numbers, just that the limit as x approaches negative infinity of f of x is L. So it's that real number. And it's similar to what we've been doing with limits, but as x goes to negative infinity means forever to the left, or x goes to positive infinity means forever to the right. So this is more of a notation we got to talk about here briefly, is that on a graph, if we're going forever to the right, what is the graph doing? And so if it's approaching a limit that's a real number, the only way that's going to occur is if the graph is somehow approaching some value. So it's converging to a number. If it's diverging and going away from, then there's not going to be a limit there. So limits at infinity. If r is a positive real number, then the limit as x approaches infinity of 1 over x to the r, it's like a rational function here, we have r as any power, is always going to be equal to 0. And if you look at that, if you have like 1 over x to the x squared, and we look at different values, so you do like 1 over 10 squared, 1 over 100 squared, 1 over 1000 squared. What happens as that x value gets infinitely large? Well, the denominator of the thing gets infinitely large, which means the fraction gets infinitely small, which means it's approaching 0. That's why the limit as x approaches infinity is 0. It's converging to 0. So if x to the r is defined when x is less than 0, then the limit as x approaches negative infinity would also be 0. And so really looking at that, where if you plug in that extremely large value for your denominator, you're getting a fraction that approaches 0. So sometimes you have operations, so the limit as x approaches infinity for 7 minus 1 over x squared. Well, you can rewrite that as the limit as x approaches infinity of 7 minus the limit as x approaches infinity of 1 over x squared. So the limit as x approaches infinity of 7, well, 7 has nothing to do with x. So as x approaches any number, 7 is just going to be 7. And then limit as x approaches infinity of 1 over x squared, that's this definition here, is going to be 0. And then 7 minus 0 is 7. So we have some other ones that are a little more complicated here. We have x in both the numerator and denominator for these rational functions. To deal with those, we can divide the numerator and denominator by the highest powered term from the denominator. So you see we have x squared in this first one. So let's multiply the numerator by 1 over x squared and the denominator by 1 over x squared. So we are multiplying by a value of 1. So we're not changing the problem. We're just manipulating what it looks like. So then we get the limit as x approaches infinity of, and this is going to be distributed to both terms in here. So then we get a negative x over x squared plus 4 over x squared all over 5x squared over x squared plus 2 over x squared. And we can reduce that. So if we reduce that, we get the negative 1 over x plus 4 over x squared. And really you don't have to reduce this if you see what's going to occur. Over 5 plus 2 over x squared. So then if we look at the limit as x approaches infinity, this term here is going to be 0, this term here is going to be 0, this term here is going to be 0, so we end up with 0 over 5, which is 0. So we can use that technique to eliminate or to create these fractions, which we can then find the limit of each portion. If we did the same thing here, I'm going to divide both the top and bottom by x squared. So if I did that, it'd be the limit as x approaches negative infinity, and then I get 4 minus 3 over x squared over 2 over x squared minus 1. And so notice how I've done the division. I'm dividing each of these terms by x squared, and then I'm reducing it. And I get this rational equation. And then that's the limit as x approaches negative infinity of, so that is be 4 minus 0 over 0 minus 1, which is negative 4. And the last one here, same thing, we'll be dividing each of these terms by x cubed. And if you do that and reduce, you find negative 1 plus 4 over x cubed over 4 over x plus 2 over x cubed. And so if you look at that, we end up with a negative 1 over 0, which is undefined. So let's talk about this for a second, what we're seeing, some of these patterns here, where this one ended up being 0, 0. Look at the problem, we had x to the first power x squared as our exponents. The next one we had negative 4, we had x squared and x squared, so the same. This one was undefined, we had x cubed and x squared. So you should recognize this when you look at the exponents and compare them. So the first one here, the numerator's exponent is smaller than the denominator, so we had a limit of 0. For this one, the exponents were the same, so then we looked at their coefficients, 4 over negative 1, which is negative 4. And in this one, they're both, actually the numerator is bigger than the denominator, so we get undefined. Those are our same rules for rational functions for the horizontal asymptote, which should make sense for these graphs, because if you think about a graph, the horizontal asymptote means the graph is going to be approaching it, but never touching it. So it's converging to that. So if I go forever to the right, the graph is going to become closer and closer and closer to that horizontal asymptote, which becomes our limit. Our y value will become that value for the limit. So there's no value for that for the function, but there is for the limit. So limits of functions can be used to evaluate the limit of a sequence the same way. So our chapter 8 knowledge of sequences can be brought in here, where just instead of using the function notation f of n, we're going to be using an, our sequence knowledge. So we're looking at, does a sequence converge or not converge? If it does not converge, it's said to diverge. It's the same thing. So you can look at the limit as n goes to infinity. So if we go to the infinity terms, we go forever and ever and ever throughout the sequence, what does it approach? Well, here, use our rules. Into the first, they have the same exponent, so we look at our coefficients. 4 over 1, so 4. For this one, it's 1 and 2, so the numerator's exponent is smaller, so it's going to be 0. And for the last one, it's n squared, they're the same, so I look at their coefficients, 4/12, which is 1/3. And it's that easy, using your horizontal asymptote rules to help us find the limit as n approaches. The last problem you talk about here is dealing with the limit of a sequence whose end term is this expression, some kind of expression like this. To deal with these, we could first simplify it, then look at our rational function. So to do this, if I first look at like n plus 1 times 2n plus 1, and if I FOIL that, I'm going to get 2n squared plus 3n plus 1. So then we need to take that and multiply it by an n value, and then divide it by 6, and then multiply by 5 over n cubed. So let's distribute 5n then through the parentheses. If you do that, you get 10n cubed plus 15n squared plus 5n. So that's distributing 5n through the parentheses. All over, and then n cubed times 6, which is 6n cubed. So now we can find the limit as n goes to infinity to see what the sequence would be for the nth term. And for that, because we have n cubed and n cubed, we can use these coefficients. So we get 10 6, which is 5/3. So for this problem, these other terms, the 15n squared, the 15n, really don't have a whole lot of meaning in the numerator because we're letting n go to infinity. So n cubed is going to be so much larger than n squared and n, it's not really affecting the numerator. So we're really looking at the coefficients, 10 over 6 to get 5/3. That's kind of like that rule. Now, some of you could see that at the beginning, if you look at the beginning of the problem here and say, what do we need to do to get the biggest degree on the numerator and the biggest degree on the denominator? And you can say to do that, it's going to be 2n times n times n times 5. And so we're multiplying that. You multiply those together, you get 10n cubed. The bottom will be 6 times n cubed, which is 6n cubed. And then you can evaluate the exponents there to see what our limit would be. And that works. There are sometimes I will ask you to simplify it, which you should practice that so you have that algebra strength still. So I'll ask you to simplify it, plug in a certain value to see the limit as n approaches 10 or 15. But then I would also ask you the limit as n goes to infinity. So that's a quick way of finding the limit as n goes to infinity, but realize what the simplifying point is. So that's it for limit as n goes to infinity. Have a good night.